I'd like to then introduce Paul, who's our next speaker. He's a senior researcher and owner of the newly established Rotterdam Office of Economy Climate Studies, which focuses on the costs of climate change, specifically damages, abatement, and adaptation. Paul started off his academic career with a physics PhD. In 2021, he completed a master's in banking and finance with a thesis focused on discounting the social cost of carbon. And any of you that attended the IAM consortium meeting back in 2022 might have seen his poster presentation. Today, Paul is presenting on how to calculate the effects of scenario adjustments. So Paul, over to you.
Hello, can you see my presentation?
Not yet.
Not yet. Do I still have to share my screen again?
Yes.
I think I did that.
It's not showing. I can share your slides. Should we do that?
I tried again.
Ah, your whole screen's appearing now.
Yes, I started. Is this a presentation?
Super.
Yes. Thank you for the introduction. I will talk in the coming 15 minutes about a way to calculate the effect of scenario adjustments on the concentrations of CO2. To the left, you see a table of a number of SSP scenarios for the rest of the century. But this is only a limited set of scenarios. Using magic is a way to transfer these emission scenarios from the left to concentration scenarios of the CO2 in the atmosphere to draw it. But what do? We want to change the numbers. For example, in SSP 4.5, at the end of the century, reduce them further. What will be then the outcome for the concentrations in that period? How do we calculate that? Of course, you can do a full Earth system modeling again, or start as emulator, as magic. But can we also do simple table interpolations? That would be the most simple way to do that. For example, here there are a few scenarios shown, emissions at the top, concentrations below. If we take another emission scenario, just one exactly between the 4.5 and the 2.6, what would be then the concentration? The first guess would be, of course, to get it exactly between, as the average between the 4.5 and the 2.6. Probably it's very close to that, but there's no need to do an extensive calculation for this one. But if you have a slightly different one, like this one, just going up and down around to 4.5, could be like that, probably. But if you have such an emission scenario going up and down, it would be very difficult to do interpolations from the tables. But still, why not? Is there a way to do good and easy interpolation from the tables? Is that needed? Yes, I think it is, but how do we do that? Now, that's the subject of my presentation today. The outline, the introduction. I will discuss the effective reservoirs method for that purpose, its calibrations, and then discuss a little bit about the replacement of data tables into coefficient tables, application to new scenarios, discussions, remarks, and summary. The physical model for the atmosphere with 3 effective reservoirs. That's the starting point. At the center is the atmosphere, central reservoir 0. It's that has a source of CO2, emission E as a function of time t, and there's CO2 transfer to and from 0 to the side reservoirs. The transfer rates H, J, K, J, they are very different for the different reservoirs, but they are constant over time. Numbers are given here. The numbers are in fact 1,000 times the probability that a gas particle, a molecule, transfer from one reservoir to its neighboring reservoir per year. Could be very high to the left, to number 1, the probability, or 10% maybe, or very low to the reservoir at right. That's the model, a physical model. Mathematically, it's written, it's as a set of coupled four linear first order differential equations. For the central reservoir, the differential equation is this one. The change in time of Y, the CO2 content, is the sum over the outflow to the side reservoirs plus the sum of the inflow from the side reservoirs plus the emission term E. The CO2 content of the side reservoirs 1, 2, and 3 it's almost similar, but there is no source in that one. So here we have 4 first order differential equations. ET, emission function, is a rather strange one, can be anything, but that one will be written as a sum of exponential decaying functions. For example, here, red one is the sum emission term. It's the sum of exponential decaying functions. To the right, here's a table of the prefactors. Constant term 5, no decay. P1 is minus 50, a slow decay, the black one. Adding all those exponentials up, you get ET. This is in fact a Laplace transform of emission. Now, this is the solution. It's the content Y of any reservoir is the sum of 3 terms. The first is related to the emission and the starting values. The second sum is related to the CO2 transfers between the reservoirs, and the third is a double sum that includes the emissions and the transfers. Note that's full of exponentials. That is an easy way, Laplace transform, to solve differential equations. Once the solution, look here, if you have a new scenario, that means you have a new set of prefactors pi, and they appear only on 2 places in your solution. And note also the solutions are linear functions. So it's very easy to change only the pi, keep the rest the same. Then you change only the scenario, but you get the outcomes for the concentrations Y. Examples. We can do that for updating existing scenarios, or do sensitivity analysis, what will happen if all emissions are 1% higher, or the effects of policy modifications, do cost-benefit calculation, or effects of unforeseen events. So that's the implication of this method of interpolation. Calibration, because we have to have real numbers. Here are data, the circles, from the literature for the atmosphere, the oceans in the biosphere, with the fitting, the calibration of this model, the full curves. And the outcomes are given here in terms of the transfer rates. There are 6 of them going back and forth to the 3 reservoirs, although the slow sink has no contribution. In fact, it can be described well with 4 parameters. The historic data, giving you the transfer rates back and forth to the atmosphere. You can apply that to the future SSP scenarios, the fast, the medium, slow. If you apply them, to the left we see medium and low emission scenarios, to the right high emission scenarios up to 8.5. But you see, they do not match well. They do not match, in fact. So the historic calibration does not work to describe the future expected concentrations. That's the outcome. Of course, we can do the calibration also on the scenarios, the future scenarios themselves. So this is the historic calibration with the full curves. If we do now a calibration where we assume that the outflow from the atmosphere to the sinks is reduced, we get the dashed lines. And they do follow the all of them, the scenario data well. it's a fitting, only changing the parameters for all 5 scenarios at the same time. So these numbers refer to all scenarios. As another possibility, you increase the backflow from the reservoirs into the atmosphere, you get the full curves as a result. In fact, you see that these are the best fit of the published data. So these can be used to study any scenario which follows a particular path, a little bit similar in this range. Just a note on the matrix H. In the left, we have the tables of the emissions, of the concentrations as published. To the right, it will be replaced by a matrix, a table H, RJ, given here in this calibration. So we replace one table by another one. What do we gain? We do. Because for giving starting time, 2020 in this case, starting conditions, levels, concentration, and for given calibration, the H matrix elements, they are the same, they're constant for all scenarios. So we have a general matrix that replaces a specific SSP table. That makes this interpolation method, this approach, affect the reservoir model more versatile than only the tables as published so far. Application to new scenarios. To the left, we have a number of SSP scenarios, emissions below, above, concentrations below. In the center, as calculated with magic, then we have the affected reservoirs model. To the top, the Laplace transforms of the emissions. They are about exactly almost equal. And below, the calculated, the solved differential equations. And you see a good match between the magic concentrations and the interpolated concentration. Of course, it should be only for the high emissions, 7.0, we see a deviation. That is a high emission. Application to a completely new scenario. We have 2 different scenarios in between the 4.5 and 2.6 here. One that it follows exactly the midway path between those, the yellow black one, and one that shifts halfway the century from the 4.5 to the 2.6, the pink one. That's the emissions. Applying the method gives us the concentrations. The midway one is indeed also for the concentrations midway between the 4.5 and the 2.6. The halfway transition is of course unpredictable, but that is the outcome. What one can see that at the end of the century, the halfway transition is 8 ppm lower in concentration than the purely midway scenario, with the same cumulative emission at the end of the century. When you transfer that into temperature, it would be 700 of a Kelvin lower with the transition scenario, but the peak temperature, 2070 about, is about 0.17 Kelvin higher. The short discussion and a few remarks. This method, you have to note that the transfer rate depends on the mean temperature of the reservoirs per scenario, and they change. In my model, the transfer rates are assumed to be constant. In principle, it's possible to do a dynamic calculation where the transfer rates change with temperature, but then you have to do recursive calculations. Also possible, but not being done here so far. It can also be used for other greenhouse gases. They have often much shorter decay transfer time, so it is easier for those. The extension to forcing global temperatures is rather straightforward. It's the same way for the concentrations as being done normally. The physical interpretation, though, of the calibrated rates remains open. Do these calibrated numbers have physical sense? I don't know, but maybe. By the way, there's no need to introduce more reservoirs than 2 or 3. it seems to work with that one, and there's no need to have transfers, to record transfers between the reservoirs. If there is in reality, if there is, it can be recalibrated by normalization, diagonalization of the matrix of the transfer functions. Mathematically, you can transfer it to effective isolated reservoirs. That brings me to the summary of this work. It's a clever ERM, is a clever interpolation to extend the set of scenarios from Earth system modeling on its emulators. It's based on the physical laws of connected effective CO2 reservoirs and the mathematical technique of Laplace transforms. Effective reservoirs method is described by a fixed matrix H plus vectors F, J, and A. It's useful for the interpolation of low and medium emission scenarios in the current century. This was my presentation. If you have questions, I'm happy to hear them. Thank you.
Thank you very much, Paul. An extremely comprehensive presentation. Can I just check, does anyone have any immediate questions? And please, could you raise your hand or pop your questions in the chat? I can see Chris Smith.
I just got a quick question. I just wondered if it's a really interesting presentation. I just wondered if the model is the model available as like some open source code that people can?
Yes, not yet. I will make it open source. I'm still testing that and seeing what's the best conditions. It will be open source. It will be even available as an Excel file because it's only numbers, fixed numbers in that.
Yeah.
So you can put in your table of emissions for each year. It has to do the fitting to the Laplace transform, and then the table converts it into concentrations. Not yet, but that's the aim.
Okay, thank you.
Thank you, Paul. Chris Smith.
Hi. Thanks, Paul. Nice to see you again.
I guess
I'm sort of curious what the sort of difference and/or advantage of this method is over, say, existing emulators, which are sort of also very quick to run and open source and sort of produce projections for any emission scenario and multiple gases.
yes. First of all, as a physicist, I would say that's it's based on a physics but on effective reservoirs. The models as fair that recursive relations in and a model, a relation which is just a first order relation. It's difficult to explain here. And the other advantage would be because, as I mentioned before, it can be just put in Excel. It gives you directly the numbers. It's only a matrix.
Okay.
Still to be discussed further, I think.
Yes, of course. Yes. Yeah, thanks.
Thank you.